Welcome to the second half of this presentation on autodrillers and top drives. If you haven't already watched the first half, you should, if you want to understand what follows. In the first part, you learned about drilling under weight control. Now it's time for drilling under pressure control, and a bit on autodrillers and stick slip and top drive controllers. Autodrillers using pressure control is all a bit more complicated. But what does pressure control mean? If there is no motor in the drill string, there's no connection between weight and pressure. But if a motor is present, then increasing weight on bit increases the bit torque, which increases pressure across the motor. Having too high a pressure across the motor will damage it, so the driller has to try and make sure this doesn't happen. So every autodriller will allow you to use pressure as the control variable, but there is an extra link in the control process, as the pressure depends on the weight, which depends on the surface velocity. In practice, drillers often don't use pressure control because of stability issues. I should add that if you are not rotating but slide drilling in a highly deviated well, then pressure may be the only measurement that either the driller or autodriller can use to control drilling, as the surface weight cannot be used to reliably infer the weight on bit. The analysis that follows is purely for rotating drilling, not slide drilling. Let's start without any filters, as before. We write the surface velocity in terms of the controlled pressure, which is then equal to the drilling equation, written in terms of weight. There's something missing, of course. We need to link the pressure to the weight. For a motor that is attached to a bit drilling ahead, the pressure across the motor is proportional to the torque, which is proportional to weight, so the pressure drop is proportional to the weight. But at the surface, as we saw in the fifth presentation, we don't measure the pressure drop, we measure the pressure above the motor. And if the pressure across the motor changes, it also changes the flow rate, which changes the pressure drop across the bit. So we need to include the fluid model, familiar I hope from the previous presentations. And as this is all about linear stability, we're going to have to linearize. There's a compliant fluid between the surface and the bit, and a quadratic pressure drop at the bit that has to be linearized. The linearized pressure response to disturbances in the system looks like a one-pole low-pass filtered version of those disturbances, or equivalently, the equation you see at the bottom. There is a parameter alpha, which is the aggregate pressure to weight proportionality that combines the bit torque over weight proportionality and the motor pressure over torque ratio, and also a parameter gamma, the hydraulic time constant of the system. So now we have two system times involved, the drill-off time and the hydraulic time. Substituting pressure for weight in the control equation and differentiating enough to get a differential equation, we now have not a second-order equation, but a third-order equation, which has three roots. Solutions are the sum of three exponentials in time, so we must check whether these grow or diminish over time, i.e. whether the real parts of the roots are positive or negative. Working out whether roots will have positive or negative real parts is slightly more complicated with a cubic than with a quadratic. There's a general theorem for this for all polynomials, the Routh-Hurwitz stability theorem, but for a cubic there's just one extra condition, and it is illuminating to see where it comes from. Let's look at a general cubic with positive coefficients, like this one. If all the roots are real, they must all be negative, because the right-hand side is strictly positive for positive x. So either there are three real negative roots, in which case it is stable, or there is one real negative root, and the other two roots are complex conjugates. And in this case I'm writing the roots as minus r and minus x plus or minus iy. If you write the cubic as the product of the three x minus root terms, you will find that a equals r plus 2x. So if r is less than a, then x is greater than 0, and the roots are stable. If r is greater than a, then x is less than 0, and the roots are unstable. Now in this case, we know that there is only one real root. So if f of minus r is equal to 0, then f is positive for all values of x greater than minus r, and negative for all values of x less than minus r. So if we calculate f of minus a, then if it is positive, then minus a is greater than minus r, and if it is less than 0, then minus a is less than minus r. F of minus a is equal to c minus ab. So for stability, c minus ab must be less than 0. If we go back to the cubic equation and work out the coefficients, this is the final stability condition. For stability, the inverse of the integral time has to be less than the product of two terms. One is the sum of the inverses of the hydraulic time and the drill-off time. These times grow roughly proportionally to the drill string length, so this term is roughly inversely proportional to the drill string length. The other term is a ratio of proportionalities and varies with the rock drillability, but does not vary systematically with the drill string length. It is clear that to avoid instability, the integral time constant must increase as the drill string lengthens. There is one additional complication which applies to drilling with a motor even with weight control and is very odd. The ROP of the system is both proportional to weight and bit rotation speed. The bit rotation speed is the sum of the surface rotation speed and the motor rotation speed, and the motor rotation speed is proportional to the flow rate. And the change in flow rate is proportional to the rate of change of pressure. So if the weight increases, there will be the following series of events. Flow through the motor is reduced, the motor rotation speed is reduced, and the rate of penetration is reduced. Now, because this is a rate of change effect, when you put it all together, the extra term looks like a negative compliance. I've used a letter psi to denote this. It's a product of a whole lot of terms. With a normal drilling system, it's not going to be anything like the size of the drill string compliance, so this term will not be negative, which would make the whole system completely unstable. That means that the same drill string will behave as if it is stiffer when a motor is present compared to when it is not. When you add this into the stability condition, it modifies it slightly, but it does not change the qualitative conclusion. So what does this behaviour look like? When the integration time is very long, the system is overdamped and takes a long time to asymptote to the final equilibrium pressure. When it is underdamped, a short integration time, it oscillates, and it can oscillate for a long time. Drilling on weight, the decay time of the underdamped system was independent of integration time. This is not true for drilling on pressure, as the oscillations are due to a different cause, the effect of having the fluid present. If the system is too underdamped, then it will be unstable, and the oscillations will grow, and then the linear analysis is not valid. Field data shows the system can go into steady, high-amplitude oscillations. If you pick the parameters inside a narrow range, where they are just right, you can get good, fast convergence. The reference where you can find this all detailed is below the graph. So now for some preliminary conclusions. Drilling on pressure introduces complications and more parameters. There are two characteristic system times involved now, the drill-off time as before, and the hydraulic response time. It is the physical, low-pass filtering process at the hydraulic response time that creates this potential instability. But of course, this is the perfect unfiltered system. What about adding filters? I won't show you the equations, just show you examples of what comes out. The analysis follows the same methodology as for weight control. There are two more dimensionless quantities, one of which is very important. The first is the hydraulic time constant normalized by the integration time, which I'm calling capital gamma. The second comes from the negative compliance effect as the flow reduces through the motor, and can be reduced to a dimensionless ratio of times, which for realistic systems is always small, less than a quarter. I'm going to plot graphs with epsilon equal to 0 and epsilon equal to 1/4, but while it affects the exact numbers, it doesn't affect the qualitative behaviour. This is the log-log stability plot when there are no filters. If the hydraulic time is less than the integral time, there is no stability line. The system is unconditionally stable. But for capital gamma greater than 1, it can be unstable. I show here the stability line for gamma equal to 2. and for epsilon equal to 0 and a quarter, which show qualitatively similar behaviour. Now for filters. First, the boxcar filter, no auto-scaling. There's lots of lines on this graph, but the ones to concentrate on are the top ones of each colour. They are in pairs, one for epsilon of 0, one for epsilon of a quarter. Each pair has a different value of gamma, the ratio of the hydraulic time to the integral time. The red-blue pair has gamma equal to 2, a long hydraulic time. The black-cyan pair a gamma equal to 1/2, a short hydraulic time. The case where without filters, it will be unconditionally stable. For the short hydraulic time, gamma equal 1/2, just as with the weight autodriller, there is instability when the proportional gain is too high, and this similarly drops off at high drill-off time. For the high hydraulic time, the high proportional gain instability smoothly joins on to the high drill-off time instability. Curiously, the system is more stable with a high proportional gain than if the hydraulic time is low. Unsurprisingly, if we add auto-scaling, the system becomes even more interesting. Remember that for low values of lowercase gamma, the system is close to a linear one. One difference between this set of stability curves and the upper ones in the last slide is that different filters are in use. The increased stability for high proportional gain with high hydraulic time is not present here. Increase the value of the lowercase gamma, the velocity ratio parameter, and when it is equal to 0.6, there is very little difference between high and low hydraulic times. The system does not have to have a very high ratio of drill-off time to integral time to be unstable for quite low values of the proportional gain. Ramp up the velocity ratio parameter further, and now low hydraulic time is less stable than high hydraulic time. At large hydraulic time, the high gain instability disappears completely, and the system is more stable for high drill-off times as well. So is there a conclusion other than it's complicated? What we really want is a more stable way of drilling on pressure, other than having a very, very long integral time, which would make control extremely slow. Of course there is, otherwise I wouldn't ask the question. The answer is to use mixed control. This equation shows normal PI control on pressure, with a proportional term and an integral term. The proportional term controls how fast the system responds to change. The integral term determines what it converges to, when it does converge. With mixed control, we leave the integral term unchanged, so the system still converges to the right pressure, but in the proportional term, we include a weight term. A theoretical analysis confirms that this increases stability, and of course it converges to the right pressure. As B over A is increased, stability increases. One way of using a method such as this would be to have B 0 until the system starts to be unstable, and then to gradually increase B as the hole is drilled to keep it stable. Determining the best WD is a small complication. It does not affect the long-term behaviour, but if PD is changed and not WD, then transients will result. Keeping WD proportional to PD should work. This method has been patented in the US and successfully tested, but appears to have stalled in the product development process. So if you want stable drilling with pressure, ask Schlumberger why they aren't selling it. I've talked a lot about stick-slip. There are a lot of anecdotes about how changing surface equipment has made stick-slip better or worse. Can autodrillers make a difference? Why might this happen? As we have seen, the bit cutting action converts some rotational motion into axial motion. This wave will then travel to the surface and be reflected, and that reflection depends on the relationship between weight and velocity, which is what the autodriller is controlling. It travels back down, and some reconverts to a rotational wave at the bit. This isn't going to be a big effect, but a small effect can make the difference between an unstable resonance and a damped resonance. It's the coupling from rotational to axial that generates the upgoing axial wave. And then when the wave comes back down, the coupling from axial to rotational that converts it back to a rotational wave. so any effect is going to be proportional to the product of these two terms. At the surface, I'm calling the reflection coefficient for axial waves Ra. If there is constant surface velocity, the reflection coefficient Ra is -1. If there was some way of achieving perfect weight control, the reflection coefficient would be +1. In general, with an autodriller, the reflection coefficient is going to be a frequency-dependent complex number, where here I am writing G for the Fourier transform of the weight filter in the autodriller. As the effect is small, we can regard it as a perturbation of the rotational fundamental, and look at the shift in the resonant frequency that results. This is in general a complex number, so a small change to both the frequency and the damping of the resonance. As well as the surface reflection coefficient, Ra, there is a phase term, the exponential of I times the frequency times Ta. Ta is the two-way travel time for the axial wave to the surface and back, and for the fundamental frequency, omega times Ta will always be about 1.9 radians. Slight variation according to the size of the BHA, but importantly, the real part of its exponential is negative. These two equations for the resonant frequency are just rearrangements, and you can see that in the particular case that the reflection coefficient is of magnitude 1, the change in frequency is proportional to Ra times this phase. If the imaginary part of the change in resonant frequency is positive, then the surface reflection makes the resonance less damped. If it is negative, then the surface reflection adds damping to the system. You can see that for a constant velocity, which includes the block held steady, a velocity of 0, the reflection adds damping to the fundamental resonance, whereas a constant weight, were that achievable, would reduce damping. There's that factor of 0.3, so the surface reflection can't remove the bit amplification all on its own. For other resonances, the effect will be different. For the next resonance, constant velocity reduces damping, and constant weight increases it. A real autodriller has a frequency-dependent behavior, and so its effect on stick-slip will depend on the exact frequency of the resonance. Well, that's all been a lot to take in. Here's a summary of some takeaways. For autodrillers on weight control, they are normally stable, but high proportional gain can make them unstable. If you use an auto-scale autodriller, there can be an additional instability mode. To optimize behavior, it will be very helpful to allow the integral time to be adjusted as well as the proportional gain. Pressure control is more complicated, and a high ratio of hydraulic time to integral time risks instability. However, there is a solution using a mixed controller. Finally, autodrillers will affect low-frequency stick-slip. For instance, constant velocity drilling will help with the fundamental mode, but it could just flip the system into the next mode. There's just one more topic to cover in this presentation: rotation control. You may be glad to hear that I'm not going to go into quite so much detail on this. I'm going to be talking about how to use the top drive to control rotational oscillations. There are two main methods of this, both of which could help, but which are unfortunately not golden bullets. The first, which I'm calling the spectral null approach, targets a particular resonant frequency, normally the fundamental. Obviously, to do this, you have to know what that frequency is. Once you do, it's quite easy to implement, but it does require access to the top drive controller parameters. The other one, trying to make the top boundary condition one that absorbs rotational waves, does not require knowledge of the specific frequency, but needs to operate an outer loop around the top drive controller, which must operate as fast as possible. Let me take you through top drive theory. This is all taken from the paper by Killingstadt and Nesion in 2009, who invented the spectral null controller. I must apologise as I probably pronounced their names totally incorrectly. You already know what a PI controller looks like. This one is controlling the rotation speed omega using the torque T. The complication here is that what is being directly controlled is the torque applied to a fast rotating mass, which is attached to the top of the drill string through gears. So there is a rotating inertia term between the drill string and the controller. When you go through the maths, the reflection coefficient for an upgoing wave is a quadratic in the frequency. This is the reference from the original paper. Here's the reflection coefficient. You can see that for given inertia, you can choose where in the frequency domain to put a minimum in this reflection coefficient, and also how deep that minimum is. So what are the drawbacks? A deep minimum is a narrow minimum. The resonant frequency is continuously changing, so if you want a deep minimum, it's important to be able to track this. Having a high proportional gain P makes the top drive responsive, so if P is too low, it will be very sluggish for the user. It only affects a narrow frequency range, so if you attack the fundamental with this, the next harmonic is unaffected. And reportedly, there have been cases where activating the control just shifts the system from fundamental stick-slip to stick-slip at the next harmonic. What has been tried is then to put in a broad shallow minimum halfway between them, which is not ideal either. Also, as we shall see, there are torque requirements to operate this. Here's an example of what it looks like in the frequency domain, comparing different proportional gains, normalized by the pipe impedance Z. The lower the gain, the deeper and narrower the notch. However, also, the lower the gain, the higher the torque requirement at the resonance. So what's the alternative? The alternative is to try and make the top boundary absorbing, and this is done by adjusting the target rotation speed for the top drive, and doing this using a filter that includes as input the actual rotation speed and the top drive torque. It looks good, but there are problems. It's quite susceptible to instability. There's obviously a lot of parameters potentially to play with here. The main issue is that filters introduce delay, and delay tends to make things less stable, not more. Low-pass filters are a necessity to restrict the bandwidth this is trying to work over, otherwise the system is trying to adjust the speed of a large rotating inertial mass at high frequency, which obviously would require a huge torque. There is also the practical difficulty of trying to optimize over many parameters, assuming that you can define what you mean by optimal. It does have the advantage you can still have a responsive system with a high proportional gain. This shows a typical system behavior for some simple filters alpha and beta, showing how delay dependent the reflection coefficient is, and also that there will always be a higher torque requirement. As you can see, this does a pretty good job of providing an absorbing boundary condition below 1 Hz, which is a drill string over about 750 meters for the fundamental, and includes the next harmonic for a drill string over 2,250 meters. However, for realistic additional delays, and 10 to 20 milliseconds is a reasonable target, there is amplification over above about 1.5 Hz. The lower the low frequency reflection coefficient, the higher the high frequency amplification, so there is a choice to be made. For long drill strings, the higher frequency amplification is not so important. With the other system losses, these higher frequencies get plenty of damping along the drill string. But for shorter systems, large damping of low frequencies may excite a higher frequency mode. As you can see on the right, the torque requirements can be high, whatever the delay. The lower the minimum of the reflection coefficient, the higher the additional torque requirement. So now finally we're done. This is the end of the discussion of low-frequency axial, rotational and fluid dynamics. The next talk, number 7, is about fluid acoustics, fluid dynamic behavior at higher frequencies, with particular application to the frequencies used for communication in measurement while drilling systems. And then parts 8 to 10 look at lateral statics and dynamics. Questions, comments, etc., as usual, the email address is on the lower right.